oscillations, let's say. Okay. So oscillations for position-based qubit. And we have this Rabi oscillations for energy-based qubit. So how we can characterize them? So basically, if the system is non-interacting, then simply this qubit has at least to energy level. So we have this way of writing the state as linear combination of projectors. And actually, to be more specific, this can be also time dependent, since we can have in general case the situation where then this eigenenergies also can be time dependent. So this is in general case. So this is non-interacting qubits. But in let's say any operator O can be written in such a way that it gives you certain, so you can write it in that way. It's an operator acting in a quantum state, right? And basically the act of and now we can consider certain processes that can happen. So so first process could be this this possibility for a quantum state to heat up or cool down. So basically, so the idea is that and anyway, your quantum state can be written in such a way that you have this linear combination of two eigenenergies, right? And more specifically, you have a situation where this is CE1 square is equal to probability of occupancy of energy level 1, and CE2 square is probability of occupancy of energy level 2. And this is a complex value. So C1 is complex and C2 is complex. So you can actually write it in that way that this is PE1, and then there's a phase, associated phase with, so you can write it in that way, plus in such a way as given here. So this is your case. And let's say I'm in the situation where so if I have such so if I have such Hamiltonian, so this is like Hamiltonian of isolated quantum system, I can see that action of Hamiltonian on my state is nothing else as, so there are two projectors. So you can write it in that way. This is a projector 1. It projects on energy 1, and this is a projector. This is another projector. So PE1 is a projector of such form, right? This projector has certain type of properties, like its square is equal to given projector, and so on, so on. So any power of this projector is equal to this projector, and obviously, two projectors acting on each other are orthogonal, so they give 0. And you're supposed to know from simple algebra such operations. So what happens is that if you act with such Hamiltonian as here on our state, what happens is that we simply have it in such a way, plus E2 right, and then here goes our quantum state is okay. I will move to another formal description just in some time. All right, so this is our quantum state. So what is the result of this action? So obviously you can observe that this state acting on such a state will produce you such situation where you have this is set to 1, so this is E1, right? The same is with such a state, E2 acting on this guy gives you E2, and then there is E2. So again, it's E2, okay? And then obviously you need to consider situations where you have such a guy, let's say acting on E2. And then what happens is simply there's E1, but those two states are orthogonal. So simply 0. And again, we have such situation is acting. So sorry, this is let's say E2, yeah. So it goes in that way, and you have it. You have it 0. So it's very important to recognize that action of this operator is preserving H is preserving the occupancy of energetic levels. So does it change the probability of occupancy of E1 or E2? Since this operator is not able to do it, right? So basically, okay, so we can have it like here. So simply, what happens is that, yeah. So that's the result of this operator action is something like that. Yeah. So this is how it happens. And then you can ask yourself, you can perform measurement on a given quantum system. Measurement is nothing else as interaction, external interaction on your quantum system. This is a measurement. Measurement on a given quantum system is connected with such action. So a given quantum system under the measurement becomes, so measurement is represented as projection on a given quantum state, and there is a normalization of a quantum state. So that's a result of this projection. So this is how it is more exactly supposed to be square root. So that there is a new case of a new quantum state that is different under this measurement. So measurement is represented by projection operator P. And this P can be, so for example, act of measurement of occupancy of first energy level is act of measurement of occupancy of energy level U1, right? So such projection. In general, this measurement can be a linear combination of projectors. So if you project this such P on your quantum state as defined here, what happens is that we have acting on a and only one term will survive. So we have such situation, and then it's so this is what happens is that only one energy level will survive. So basically, the situation is quite boring, is that after this measurement, your state is basically some phase prime and given energy, eigenenergy. So you can make measurements in energy space. You can make measurements in position space. You can make measurements in momentum space. So so for position-based qubit, one can do measurements in energy space, in momentum space, and in position space. Well, not only for position-based qubit, but in particular for position-based qubit. All right, and now there is issue how to move. So we have this isolated qubit. There's nothing else as K1 plus N. And then we have this Guy's reasoning in such a way. This is the most abstract theoretical representation, projector representation, and this representation will have its advantages, various form of advantages, and you'll see why you'll have advantages quite soon. So this is Hamiltonian of isolated quantum system. All right. Well, what we can do further, and then we can have this situation where we are acting. We want to change the population of eigenenergies that are occupied, and basically we can a resonant state. So now I will consider some hypothetical state which has such form f of t, and it has a form as given here. So how it behaves? It's if let's say if your quantum state initially has only such value as is only one times this so we have this so when it acts, it's what happens. So we have a situation when, one moment please. So we need to inspect how it acts. So f of t, okay, acting on this guy is nothing else as plus 2e1 and acting on e1. So what happens is that it will have a property of inverting, so the state population. So it is changing the kind of ground state to excited state. So we see that it has property of inverting the quantum state. So this is how it can be written. Yeah, and intuitively we can also consider, so this was the first case, and the second case could be this this quantum state can be excited state, what will happen when this term will act. So f of t, yeah, so yeah, and then we have the situation where the excited state is turned into ground state. So this is picture. So we see that inversion of energy levels are achieved with resonant state. So what happens is that we might suspect, it's natural to suspect that it will flip certain occupancy of one energy level into another energy levels and back and forth after a certain time. So perhaps we can, so what type of equations of motion we have? Let's say we, d over dt, this is our equation of motion. And there is Hamiltonian times given quantum state. Yeah, so how we can proceed with such well, obviously, so we can write this in a kind of more tricky way. So at time 2 is and then there is 1 over h. And there is this quantum state at 1. Anyway, there is dt, right? Okay, so so if we have this, our initial occupancy, so let us see that there will be specific equations of motion. So if our quantum state has such coefficients, let's say, they are going to change after this evolution. And this so it's also interesting to see this representation of the state. So in terms of matrices, it's nothing else as 0, 0 on the diagonal and f on anti-diagonal. Well, this is f of t, right? Well, you can study this these terms. Okay, so this is anti-diagonal, and now it's a question whether you want to have a time-dependent Hamiltonian or time-independent Hamiltonian. So f of t is like an enveloping function. And just to bring you a reminder, so isolated qubits, so this is in energy representation, so this is in base E1, E2, right? So we have E1, E2, and this is, so this is in such a base, E1, E2. Yeah, but you need to analyze things in more detailed way. Why I'm saying that? Because actually it turns out that if you have such, let's say, let us re-examine this Rabi oscillation term. So if you have f of t, and then if this is time dependent, there will be certain time factors. So this will be d time t, and here will be minus 2 times. Okay, so let's say, so you can have 0 here, plus. So actually, in a more general way, you can set f to be complex value function, but then you need to have more specific structure. I'm just going to present you right now. So this is ht, and you want 0, and there is such term, right? So when you move to a description of position-based qubit is, yeah, so basically if you have such matrix, this term is proportional to such value. This term is proportional to such value, and this one is converting from E2 to U1, and this guy is doing reversely. Right. So doing so, you can write your Rabi term in the following way, and then you have zeros, and then you remember about this guy. So this is f of t, and there is this t, and then there is ft given in such a way. Right, so this is your Rabi matrix, Rabi oscillation. So clearly, you can see oscillating. It will turn out that in order to be effective, the most effective is radio frequency field that has frequency of oscillation that's nothing else as an energy difference between energy level 1 and 2, and it's shining such type of light or having the antenna activated with radio frequency signal of such frequency, you're able to manipulate the levels of this qubit. Yeah, so perhaps we're supposed to re-examine this step in greater detail. All right, so let's say, yeah, so what happens is, so we have such situation, U1 plus delta T, EH. Yeah, and now we just only consider Rabi term. Oh, sorry. Yeah. Okay, so maybe I will write it in a such form. So I can always write C2 as T1, right, as such a vector. So simply what I will have here is I will have time T2, which is basically t plus delta t plus delta t, and then I have such a vector at time t, and there is this rabbit term. So I replace delta t over h, and now we have our matrix. So what we have is this guy, E1 minus E2 over, yeah, and then again, Hermitian conjugate, complex conjugate, so we have over EH 0, and again, we have this term, that's T1. All right. So if we now, so we rewrite this equation in a kind of subtle way. Yeah, well, so what we have is t plus delta t is equal to, and then there is this ability of this inversion, which I have already mentioned to you. So this is ft e1 minus e2 t over eh ce2 e1, and in a logical way, we have the change of occupancy of energy level 2. So this is nothing else. Again, the same procedure, but then we have this complex conjugate U1, U2, C. Yeah. So we have a such type of situation, and actually, why not to go to have such set of equations, and you see that C1 over dt is nothing else as the h f of t, and then we have this, yeah, C2, right? This is first equation, and there's the second equation, which is nothing else as this guy, and there is E1 minus E2 T E H CE1. Yeah, so you can ask yourself, you can compute second derivative of both guys. So basically, and it will give you nice oscillations. So yeah, I will apply the over dt operator here, and here the over dt. Okay, so let me see this in greater detail. So this square is u1 over dt square, and then first I act on this guy. So let's say ft is constant, just for simplicity. So what I will have here is I will have minus e2 f of t c2 plus this guy f of t and u1 minus u2 over H. And then we have the over dt C1, right? And then I can simply see, yeah, so I can plug it here, and yeah, so I can move on with such equations of motion, and then you can simply, yeah, actually it's even simpler to be like that. So say if I place C1 here, I will have harmonic oscillations between eigenenergy levels. So I have this C1 is this C2 over dt and H1 over F. Yeah, so this is, yeah, I can write it in that way. Yeah. Okay, so let me move on with so we can reduce second ordinary differential equation for C1 and C2. All right. So the next point is that what is the role of this our terms? So basically, so clearly our interpretation is that we have this term. This is cooling down of quantum state, and this term is heating up the quantum state. Well, we recognize that this is how to say, yeah, so this is heating up, and we recognize that this is non-Hermitian operator. This would be okay. Yeah, so non-Hermitian operator, and again this is non-Hermitian operator. So it's quite obvious that heating up the quantum state or cooling down the quantum state is like injection of energy or subtraction of energy. All right, and now we are arriving into this. So in general, this qubit, this position-based qubit in a radio frequency field is nothing else. It's Hamiltonian, could be written in such a way that we have E1, E2, and now we have our terms minus E2 over EH t, and we have our terms E1 minus E2. Right. So this is of such form in eigenenergy representation. So then the question is how to implement such type of system. And And the idea is that you have your silicon, and then you have this insulator, and then you have gates, G1, gates G2, G3, and you bias these gates to certain voltages. So if your quantum state is kind of trapped here, then you can generate time-dependent potential. And it's very interesting that what you expect is that you would expect that this time-dependent potential will absorb or emit a quanta of energy that is proportional to this energy difference between energy levels, as it's written in a Rabi oscillation term. Okay, so basically, yeah, so yeah, just it's a kind of homework to get these oscillations from this state. Maybe I will come to this issue in some future. Anyway, what you need to do is to compute the over dt C1. So remember, we want to approach such term, but we are using yeah, this term. So yeah, so I believe you can deal maybe yeah on your own with such problem. Okay, so let me move to this problem of Rabi oscillations and radiation. So so the idea is the following, that we have resonant cavity and we can have either a resonant cavity with a hole. So this is our resonant cavity. And you know, this is resonant cavity, this electromagnetic resonant cavity. And it can be a hole, and then you can place your position-based qubit in a certain distance. And then what you can have is you can have interaction of matter and radiation. So you can have some effective potential, and then there's this interaction. And then there's issue how to represent this interaction in greater detail. So, okay, I will write for a cavity. You have cavities are like a little problem, bit similar to problem of harmonic oscillator, but for electric magnetic field. So this is kind of safe energy of electric and magnetic field. And so this is analogical to your position, and is analogical to your momentum. So virtually it's like harmonic oscillator. So what you have is kind of something like that, right? Did you know that in such harmonic potential, the difference between eigenenergies is constant? So you have a very nice feature. Is some constant value. So you expect the same from quantum resonant cavity. And this quantum resonant cavity is interacting with your position-based qubit. And the question is how to describe this interaction in greater detail. So there is, so we have this cavity qubit. Is a proportional to dipole moment and electric field. Dipole moment. Dipole moment of position-based qubit, and this is electric field coming from electromagnetic field. So obviously we consider the most simple case. We consider the case where this there's no dissipation in cavity. There's no dissipation in position-based qubit. So yeah, so basically what we have is the Hamiltonian level system is, let's say, cavity Hamiltonian. Yeah, so this is identity, a qubit, plus cavity times qubit, plus this interaction term, which joins both. So this will be cavity qubit term. Yeah. So let's say most minimalistic situation is where you have at least two eigenenergies in cavity and two eigenenergies in a qubit. So, okay, so let's say your cavity will be this V1, V2. Let's say such thing as here. So matrix 2 by 2, right? And this qubit is also 2 by 2. We already discussed it before. And now this most tricky part is this interaction. So what will happen during this interaction is a matter of some postulate as well. So this cavity qubit interaction. Okay, I will denote some function g. So what we expect is that, let's say, during interaction, this, let's say, qubit will go to, okay, so during this interaction, the qubit so we can have this proceed, okay. I will call it, sorry, it will be easier to call it C cavity 1 and cavity. So this, there will be two terms. So there will be exchange of energies. So this, so either okay, I will maybe write it in greater detail. Either this qubit which was in excited state goes to the ground state, but at the same time the cavity which was in a ground state goes to excited state, or reverse process, which is basically you will see just give me a moment. Yeah, so this is like, this is interesting. So this is like so this is like annihilation operator, this part, annihilation operator, and this is like creation operator. And reversely, this is like, again, creation and annihilation operator. Why is that? Because, see, if I want to say that I am destroying, I'm annihilating the state at E1 and creating a state at E2, it's nothing else as this such type of representation. And here I can have a scenario where, yes, annihilate state E1 and creates, so this is basically this type of representation, right? Okay, and yeah, and the question is, so you can recognize that there's interaction since there is energy exchange between two quantum systems. So first level of approach is that this interaction is of perturbative character. So it's an interaction between position-based qubits, or like single electron and electromagnetic cavity. It's open issue whether you want to place this position-based qubits inside the cavity or slightly outside. Outside, you need to make a hole, and there is a weak of radiation, so there's some dissipation. Again, if you place a qubit directly in the space of a resonant cavity, this qubit will also generate some perturbation of electromagnetic field distribution. It's a bit type of hard problem. Anyway, so what is our Hilbert space for this problem and how to tackle this problem? I will give you just in a second. So, yeah. So it seems to be obvious that, okay, let's say in the quantum state has at least 4 energy levels. So there is a possibility that C1 is cavity. Cavity and qubit are both in a ground state. And then there is a possibility that, let's say, this cavity is in a ground state and the qubit is in excited state. And there is a possibility that cavity is in excited state and a qubit is in a ground state, and both. We have this C2, E2, right? So we have 4 configurations in energy space. This is under certain rigorous assumptions. Such state of quantum system is represented. It can be represented in such a way. And now, yeah, so we can have it so clearly, we can write it this guy as in such a way. Yeah, so, and so on, so on. And now we come to this idea of entanglement between matter and radiation that will be very essential for our quantum communication. All right, so how to go greater detail in such description. All right, so basically, I will try to keep combined. Okay. Sure. All right, so what we had so far. So now we need to represent such type of operators, and okay, maybe at first is this term cavity times qubit. So it's basically AC1, AC2, 0, 0 times 1. Such type of guys. So basically what we have is C1, C1, C2, C2, and zeros otherwise, right? Then we have this term where there is cavity 1 and times a qubit, and so what we have is such a situation that yeah, E1, E2. So we will see later that the Trabi oscillations are naturally built in the system. Okay, so this is basically E1, E2, E1, E2. All right. And then there is this interaction. There is this interaction between matter and radiation. And there's also entanglement that takes part in this. Yeah, so we need now to so to be able to represent it, so I maybe write this. Okay, so what we have is we will see. So it's not hard to recognize that this interaction term is generating this entanglement between matter and radiation, and so what we have is that we need to be able to evaluate those guys. Yeah, I already did it here. So I just need some so we have 0, 0, 1, 0. So this is this term. All right, so we gotta write it down, the whole cavity qubit. So what we have here is, so we need to that's part of this algebra. So so what we have here is this guy, and yeah, so we also have this guy. So let's say let me first write it in that way. So 1C, and then we have 0, 1. So we have this 0, 1, 0, 0, and such guy. And such guy is nothing else as E2. So this is 0, 1, 0, 0, right? So what we have to write it to see E1 times E1C E2. Yeah, is yeah. So what we have is and then okay. So what we have here is this guy, and this guy is this guy. So we have a matrix like this: 0, 0, 0, 0, 1, 0, 0, 0, and 0, 0, 0, 0. Yeah. And yeah, we can expect that this matrix is Hermitian conjugate, because those terms are Hermitian conjugates. So in general, maybe we can, so we have a qubit Hamiltonian. Yeah, so we have this EC1, EC1, EC2, EC2, plus E1, E2, E1, E2. And this is important that this non-diagonal terms will generate entanglement. So basically we have this G1, 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 yeah. Yeah, so this is our interaction of matter and radiation that needs to be translated in greater detail. So what is important is that if we compute the eigenstates of such matrix, these eigenstates will be entangled states. So it's so this if stronger is this interaction of matter and radiation, the stronger is cavity-qubit interaction, the more entanglement we have in the system. And I will not go into greater details, but basically, if we place, what happens is that if we have this issue, the possibility, which we'll describe in greater detail next coming meeting. So this is qubit A and a qubit B. So this, and this is quantum electromagnetic cavity, is simply that what happens is that this guy is entangled, and this guy is entangled, and because of that, happens that qubit A is entangled with qubit B. So affecting the state of this guy, qubit B, or result in change of state of qubit A and reversely, and in such way this teleportation will be possible. And this teleportation is, it's a basic kind of feature of a quantum communication. So whenever this teleportation is taking place, there is a possibility for having this quantum teleportation. However, to tackle this problem in greater detail, we need to how to say, we have to consider the interaction between, so basically we need to deal with 8 by 8 Hamiltonian matrix, and this is most minimalistic. Still, this Hamiltonian matrix can be easily solvable. So just to make short summaries, okay. So the total system is, let's say, a cavity times E qubit A, E qubit B, right? Plus what we have here is the qubit cavity is qubit A, right? Plus, this is so far for non-interacting cases. And then we have we have this cavity and qubit A times H qubit B, right? Right, so that's our, so this is for non-interacting parts. So I call it 0. And now we need to have this interaction. So how this interaction is taking place? I will simply consider this cavity still to be two energy level, C1, C2, right? So, and there is possibility of exchange of, so let's say, so there is certain strength of interaction of qubit B with, okay, let's start from qubit A. So we have this C1, C1 E to B to A, right? So there is exchange of these energy levels. To B, sorry, 1A. It's kind of, unfortunately, it's a kind of lengthy class. Yeah, and everything needs to be reversed. C2, IA, and this is C1 to A. And of course, times identity for qubit B, plus, this is unfortunately lengthy animal, so, and then, we have all these terms, but we need to remember about identity So let's say EA, and again it's a bit similar, but this is C1 to be C2, 1A, 1V plus C2, 1V, C1 to be, yeah, and then, yeah, I'm just looking if I didn't miss anything. EA. It's quite interesting to see that what is identity in this energy representation. Okay, the projection of state on itself. So let's say qubit A has such representation, and qubit B has such representation. So we have the sum of two energy projections. This is this. Anyway, I'm not going to discuss all these aspects in greater detail. I just want to signalize you how to construct this matrix 8 by 8, and then by your own you can dig out all this. You can dig out all these dependencies. So you can search for eigenstates of the system, and you can search for a quantum entanglement. All right, I suggest we go into more technical parts next week, and then so maybe I take questions at that stage. So please give me some questions. And just would be nice to. So yeah, so basically that's the most simple approach. Maybe I will specify certain detail coming week next week. So, and then I will move to other topics that could be even more exotic. But let's say this quantum communication is important because this is really what works with quantum technologies. I attach you this one of my papers on possibility of implementation of quantum internet in a CMOS single electron devices. I send you by email. Perhaps I will have a chance to discuss certain details of this paper. Yeah, so all right, so if there are any questions, I suggest we continue this discussion next week, next Friday at the same time. And anyway, thank you for your attendance, and hopefully see you next week. All right, thanks.